I thought I had to switch on my video despite the bandwidth issues to demonstrate, as Sri noticed, that my appearance has changed somewhat, for any of you who don't already know. Apologies in advance for the slightly cheesy title. I just can't help myself. There is listed here are a series of contributors for information that went directly into this presentation, but I want to acknowledge that there is a very large team of people who've contributed to this work, 13 different researchers, and I'll try to make some reference to them as I go through the presentation. So I wanted to start off with a little bit of scene setting. So the big picture for heat in numbers. So it's about 50% of total demand. And even if when you compare all of the other types of demand that we have on energy, we have very small amounts of renewable sources going into all of these different energy vectors. So there's going to be a lot of competition, especially when you compare this to, sorry, I'm just trying to get my pointer, especially when you compare this to the domestic demand, say for space heating, which is represented by this natural gas line on this energy chart at the top right here, for heat. And at the same time, we're doing a lot of this. We're doing a lot of burning stuff or heating stuff up in furnaces. And we have to acknowledge the thermodynamic constraints of the material that we're trying to produce. So we've got things like the melting point, and another key temperature would be the austenite to ferrite transformation, which is important in dictating the properties of the material so that they are actually useful to us. And you can hear more about that from Mark tomorrow. But there's opportunities and threats. So we're producing, as Sri highlighted, for an integrated site, something like 20 petajoules per annum to the largest vector. And that's about the same energy uses as to heat 500,000 houses, which would otherwise consume about 1.4 megatons of CO2. So there's a significant role that steel can play, both in reducing its energy use, but also in potentially harvesting the energy or the heat that it does generate and using that for the benefit of the wider society. And there are economic imperatives within the steel industry to do this as well. So it's a huge challenge, as Jeff has pointed out earlier on, and we have limited resources. So we have to try and target this as best as we can. So what are we doing? We're taking a two-pronged approach in this particular area. We're looking at how we can try and solve issues around demand. So this is a steel ladle. It's lined with refractories. So the insulation and keeping the heat where we want it is extremely important. And that's a key focus of this activity. And the other thing is that when we try and generate heat via whatever source, we need to try and get it into our material as efficiently as possible. And that's another focus from a demand perspective. And then from a utilization perspective, we're examining two key technologies. One is around extracting that heat, that high grade heat that Sri talked about from surfaces, solid surfaces, and turning that into electricity. And the other one is looking at how we can look at these maybe slightly lower grade heats that might come from gases or other outputs, and how we harvest that for interseasonal and mobile heat storage to try and benefit the wider community. And ideally what we'd like to try and do is pull these two threads together so that we're able to link the utilization with the insulation, and look at the impact of heat transfer efficiency in charging and discharging of some of these technologies for making the heat that we generate in our industry more mobile. So how is this sort of knitted together as far as this task is concerned? We have some core activity which is funded by SUSTAIN that supports a PhD and a postdoctoral researcher who's looking at refractory characterization and use simulation. And then we're aligning that to a series of different activities which have allowed us to generate some nice case studies, of which unfortunately I'm only going to be able to discuss one today, to demonstrate how these are actually have some tangible benefits for the industry, and an area around a near net shape production of thermoelectric generators. And there are two new exciting activities which I'm only going to touch on very briefly, just to tell you that they're happening, essentially around improving this heat transfer efficiency and reheating, and looking at how we can democratize the heat that's made by the steel industry. So what are refractories in the steelmaking context? They're essentially rocks glued together with carbon, a combination of phenolic resins and graphite. And one of the things that we thought we'd learn from is an analogous system, which is rock stuck together with carbon, and that's soil. And what we've demonstrated in our advanced imaging of materials facility in Swansea University through both X-ray CT and other multimodal imaging techniques is that we can understand a lot more about these types of systems by looking at their 3D structure and how they're arranged. So we wanted to look at what does that look like in the context of refractories. So on the left-hand side of the screen here, you can see a fly through of these are a series of slices going through a refractory. These are the rocks. In this case, it's alumina. graphite or alumina carbon system, and the bright spots here are some zirconia material, which is used for toughening and improvement of thermal resistance to thermal shock, and I'll explain why that's important in a minute. And then what we can do is look at how we segment that those different components, and through quite a long series of optimizations, we've been able to get pretty close, once you account for the porosity, to the calculated values that we have there. But one of the problems that we have, so to acknowledge that and be honest about it, is that whilst we can see the binder, the detail of what is happening inside that binder, i.e. the difference between the way that the graphite is behaving and the resin behaviors, is much more difficult to define. So we can see this with our eyes, but getting the computers to see that and digitally segment that is becoming more challenging. So we need to look at a range of other techniques that we can use to be able to help us visualize that and understand how that component of the refractory is behaving. Which leads me on to our simulation approaches. So at the same time, we're developing approaches for simulation, physical simulation of how those refractories are actually behaving in service. And we're doing this through an approach of increasing complexity. So first of all, we're looking at atmospheric degradation of this material, so how it oxidizes. And it's particularly susceptible to this because it has this carbon in there. Now, you could argue, why is the carbon in there in the first place? And that's because we need to, ironically, increase the thermal conductivity of the material to a degree to account for the fact that a lot of the applications are in fact transient. So imagine a ladle being filled full of molten steel and then emptied. And we need to account for protecting against thermal shock. And then, of course, if we are putting these molten materials in contact with these refractories, we'll also in the future need to be able to understand how they react with slag, molten slag and molten metal. And that's something that we'll move on to later or further down along the project. But just to give you an idea of some of the outputs from the atmospheric behavior of the material, what we've been able to do is to develop, using thermogravimetric analysis and some of the heat treatments that we've been doing, a method to rapidly assess via non-isothermal, i.e. Through continuous heating rate and model free kinetics, so a simple and easy to implement kinetic approximation of the material, how the activation energy or the barrier to oxidation in these materials is changing as a function of the conversion. And this is quite interesting, and sorry for the technical bit, because if you look at the way the materials are profiled at the moment, they're either profiled just in terms of how they enter the supply chain or at some fixed point. And generally, the types of activation energies that are spat out for the sorts of degradations of these materials are up here. But what we've noticed in the experiments that we've done is that they slide off quite quickly, and that's a function of the increasing levels of porosity that are generated as you degrade the material. So to try and understand what's controlling that degradation, we've entered into a nice collaboration via the Royce Institute with the Materials Research Facility at Culham. And what we've been using there is their in situ and ex situ Raman capabilities to look at how the degradation of the material changes as a function of this conversion. And what we can see by analyzing these peaks, without going into too much technical detail, is that the ratio between these two peaks here, the G peak and the D peak, give us an idea of the increased levels of crystallization in the resin and the increased level of ordering that we get and degradation that we get in the graphite. And what we've been able to do is correlate that directly to the oxidation behavior. And that's quite useful for companies, because now what we can do is use a relatively rapid scanning technique to look at how the materials are behaving and degrading. And what's interesting about that is that we're actually able to do it in a spatially resolved way as well, which is neat and fits back into some of the challenges that we've seen with our X-ray CT analysis of these materials, because it allows us to differentiate on a spatial basis between the graphite and the resin and how those two things are being attacked. And we're now moving on to look at how we can connect that back to the X-ray microscopy and learn much more about how these materials behave. Why is that important? That's important because if we can improve the resistance to oxidation, we can remove some of the carbon, still maintain our thermal shock resistance, increase or reduce the thermal conductivity, and increase the thermal efficiency of the process. And this can have very significant effects when it's multiplied across an entire steel plant. The next thing that I wanted to touch on in a little bit of detail was the thermoelectrics work. So a brief reminder of how thermoelectrics work. You have N-type and P-type legs. And if you put a heat gradient across those, then you get the movement of the electrons and the holes from the cold side to the hot side. And if you open circuit that, you'll get a voltage. And if you close that circuit, you can get a current, and then you can generate electricity. But if you look at how these are conventionally produced, there are some challenges because they tend to be large, flat, and quite stiff with ceramic on either side, if you've ever pulled apart, say, a fridge from a car, for example. Now, what Matthew and Geraint are doing is looking at a novel method of producing these. Matthew's looking at how we synthesize the materials, and Geraint's looking at how we can optimize the morphology of these materials and improve the binders that we put in, which has nice analogies to the stuff that we have to do in refractories. So hopefully with my bandwidth issues, this video is coming through. But what do? They mix up all of the ingredients. Oh, I've stopped it. They mix up all of the ingredients in a pot. They put it in a mixer. It comes out as a nice little black sludge like that. They take this black sludge and they pour it into a little mold, which could just as easily be, say, a hole in a refractory mold. And that's something I'll come on to later. Cure it for 2 hours, take it out of the mold, stick it in this machine here, which measures both the thermal conductivity and what's called the Seebeck coefficient, so how much that voltage in that leg changes as a function of the temperature difference, and then build devices, put them on a hot plate, and look at what sort of power output that we get from those materials as we heat them up. So how are we getting on? Well, the very early crude cases were producing about 20 microwatts, and that sounds tiny, but just let me finish. What's interesting about this, and this relates to the opportunities that Sridhar highlighted, is that we're able to potentially produce self-powered sensors, which would allow us to track the temperature, for example, of a ladle as it goes around the steelmaking process, which could be driven into some of these data-driven innovation approaches to look at better thermal scheduling, for example. And the nice thing about them is that they have nice efficiency peaks, which are a function of that Seebeck coefficient and thermal conductivity, the ZT value, that correspond nicely to what our ladle shell temperatures are. So we're looking at that as an immediate opportunity. And in terms of the work Geraint is doing, he's been able to optimize not only the geometry, so fat things have higher voltages but lower current, and thin things have higher current but lower voltage, but also carbon additions. Again, nice analogy to cut to refractories there, to look at how we can optimize that to improve the performance of these generators. So what's this kicked out at the end? Well, now they've been able to generate not just a P-type, but also an N-type bismuth doped material. They've put that on a hot plate, and even at the extremities, it's now producing something like about 7 times the power output of the individual legs. And this is incredibly useful to us because not only do they have good power density, which is well linked to the sorts of applications that we're interested in for steelmaking, but also we can cast them into any shape we like and integrate them into any device that we like. So those are some nice technical outputs. And then I just briefly, as I said, wanted to introduce some of the work that we're just starting now, which is quite exciting. So there's some emissivity work going on. So if we have to heat our materials over 1,000 degrees and harness this useful phase transformation, then at those temperatures, the emissivity becomes incredibly important in determining the heat transfer efficiency. And what we've seen in the past is that different levels of oxidation can give you different emissivities and therefore different efficiency of getting the heat into the material. So what Holly at Swansea and John at Sheffield are working on is being able to link those two activities together so that we can understand more about the relationship between the emissivity and the oxidation, and then be able to optimize the heat input into the material. So we're already charging instrumented slabs into industrial scale reheat furnaces, using that information to inform some TGA experiments on oxidation, and then first ex situ and then hopefully in situ measuring the emissivity changes as that oxidation changes. And what's nice about that is some preliminary work that we did in this area will allow us to link into some data-driven innovation work that's going to be presented by Michael, I believe tomorrow, where you can see how this might have implications for AI control of processes. And then very finally, with my last 50 seconds, I just wanted to highlight the work of Jonathan Elbins. He's done this really interesting work developing a heat storage material, which is essentially a salt-in matrix material, which if you pass warm, dry or hot, dry air over it, will charge endothermically and then discharge exothermically when you provide cool, damp air, which we have lots of in Wales. He's done that in the context of active buildings already, but now what we're looking at doing is seeing how we can tailor that specifically to get heat storage from the steel industry. And the nice thing about this is it's nice and light, it's easy to transport around the area, and we're looking at being able to utilize industrial heat for the benefit of, say, domestic or other industrial space heating applications, and make sure we make best use of the heat that we still may have to lose. So we've developed some nice characterization methods, which we've used on three case studies, and I haven't been able to present all of them today. We've got some nice near-net shaped thermoelectric generators that we might be able to integrate into the linings. And work is starting on two new exciting projects looking at the thermochemical behavior and the heat efficiency. And we'll be working with the guys in the data-driven innovation team to see how we might be able to make best use of the data that we're generating to optimize the process from a data perspective. Thank you very much.